Hey, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Let's jump right into it. Okay, so highlights from last time. We spoke about things called critical points. This is where the derivative of a function is undefined or equal to 0. We know these are two important cases based on Fermat's theorem and examples like absolute value of x at the origin. So we're going to want to know where this happened because at points where that happens are prime candidates for maximums and minimums. So that we define critical numbers and critical points. And we looked at the closed interval method, how you can find the absolute maximum or minimum of a function, continuous function specifically, on a closed interval. Such features are guaranteed to exist by the extreme value theory, which guarantees that if a function is continuous on a closed interval, it will have an absolute max and min on that interval. And I told you the process of that. You're going to find all the critical points. You're going to evaluate them because they are the prime candidates for maxes and mins, as well as evaluate at the endpoints because the function can achieve a max or a min at the endpoint that a derivative won't be able to pick up. You're going to compare all these values. The biggest one is the absolute max, the smallest one is the absolute min, and I left with an example to try, and that is where we are now. So we're going to do this. Happy 420. By the way, let's actually finish this. Let's finish up this example. Come on, iPad. All right. So first of all, you should note that this is a polynomial. And so it's definitely continuous on this interval. In fact, it's continuous everywhere. So the first thing I want you to do is note, it's coming in here. F is a polynomial. So it is continuous everywhere. So in particular, it is continuous on this interval. So EVT tells us that absolute extrema occur. Okay, and by that I mean both absolute max and min. Okay, that's going to be guaranteed to happen. Now, how do we actually go about finding these? We use what's called the closed interval method. So we are going to, step 1, find the critical points. Okay, so now remember what critical points are. This is where the derivative is 0 or undefined. So we are going to take the derivative of this, which is 4x cubed minus 8x. And then now for critical points, set f prime equals 0 or f prime undefined. F prime is actually a polynomial, never undefined. And so the only thing we have to look for here are the points where f prime is 0. So this will tell us that this means that 4x cubed minus 8x equals 0. And that's an equation we can solve because we've been through pre-calc, so we can factor out the common term. So this means you have, say, 4x times x minus rad 2, x plus rad 2. So this means x equals 0. x equals rad2, x equals minus rad2 are the critical points for the critical numbers. As I mentioned, we say critical points sometimes, we mean critical numbers, it's fine. By the way, not all of these are valid. We're on the interval -1 to 3, and if you recall, the steps say you want all critical points that are in the interval. So we only care about being on this interval -1 to 3. You will notice that this guy is not there. It's not in -1 to 3, right? Because this guy is roughly, -1.4. So there are really only 2 critical points to test, and we're going to test them. So this implies we want to test f at 0, which is going to be 0. We also want to test f at rad2. Now, f is x to the 4th minus 4 times x squared. So it's going to be that. Raising to the 4th power means squaring and then squaring again. Raised to the 2, raised to another 2. So you square radical 2, you get 2. You square it again, you get 4. Rad2 squared is 2. 4 times 2 is 8. So this is -4. So we've just found both. We evaluate we find the critical points, and then we evaluate the function at the critical points. Okay. Now, what we do, the second step, is to test the endpoints. Now, the endpoints are the -1 and the 3, the endpoints of the interval. So I'm going to pretty much do f of -1 and f of 3. So f of -1 is, I'm going to plug in -1 to the 4th, -4 times -1 squared. It's 1 minus 4, and that's -3. And then f of 3 is going to be 3 to the 4th minus 4 times 3 squared. If I factor out a 3 squared, I would end up with a 3 squared here, -4. So 3 squared times 9 minus 4. 3 squared times 5. That's 9 times 5, which is 45. Okay. And now finally what we do is the third step, we compare. You want to go, and out of all the y values that you found, which are these guys right here, f of 0, f of radical 2, f of -1, f of 3, you're going to pick the biggest and the smallest. So the smallest, it seems here, is this guy. And this is the smallest. And the largest is this guy. So that sort of tells us what is our absolute max and min here. So remember, we state them as equation. We can say the absolute max is f of 3 equals 45, and the absolute min is f of radical 2 equals -4. And that is your answer. Okay, so that is the process, a 3-step process. That's everything if you can read that. So you find the critical points, you test the endpoints, and then you compare. Okay. Now, I want you to appreciate what's happening here. So let me just illustrate the situation for you. What do we actually have? What is actually going on here? So we know how to sketch this from pre-calc. So let's actually do a little sketch. We have our y is equal to x to the fourth minus x minus 4x squared, right? Yes. Of course, this means I can factor out an x squared. I'd be left with x squared minus 4. Factor that into x minus 2, x plus 2. So that tells me x equals 0, x equals 2, x equals minus 2 are the zeros, or the x-intercepts, as they might be called. So I know the graph passes through here, passes through minus 2, passes through plus 2. That should be. That should be somewhat symmetric. We know from end behavior, this is a polynomial with an even power, so I know both endpoints go up because it has an even power and a positive leading coefficient. In between that, though, I would just test some numbers, some random numbers, say minus 1 and 1. If I plug in minus 1 into x to the fourth minus 4x squared, or I can think of also plugging it into here, the factored form, which is probably easier in general. Notice that the x squared is always going to be positive, so we're really going to have to check the signs of the x minus 2 times x plus 2. If I plug in minus 1, I get minus 3 times positive 1, and that's negative times positive, which is a negative. So I know the graph should be down here. And if I plug in a 1, I would get minus 1 times 3. So I would get, again, a negative times a positive, which is a negative. So I know the graph is down here. So ultimately, our picture is going to look something like that, right? But we don't want the whole thing, right? We just actually want on the interval minus 1, 3, what is it that we actually have? So it's like I'm taking this W, right? I know that this this point right here happens at minus rad 2. I also know that this point right here happens at rad 2. And so minus 1 is going to be somewhere like here, and 3 is going to be give us somewhere up here. So what you'll realize that we have then is a graph that looks like this, because I only care about those points, right? So it's just a piece of the W, right? That piece right there, that is between minus 1 and 3. And then there's a rad 2 right here. And now you can actually notice why the absolute min is where it is, why the absolute max is where it is. If you look at the picture, that's definitely your absolute min on this interval. And that point here is your absolute max. So I know the absolute min would occur at radical 2, and I know the absolute max would occur at when x equals 3, right? And notice that I knew that before even graphing anything, because not always are you going to be able to graph stuff. Some functions don't even have very nice graphs. It will take forever. But to actually locate where these points are, you can use derivatives via the closed interval method whenever your function is continuous. Yeah. So yeah, this was the point, rad 2 comma 40 minus 4. This point here is 3 comma 45. All right, so that's that. Now the problem didn't ask you to sketch it. I just sketched it just so for you to have some kind of intuition as to what we were actually finding, what we're relocating. So now we are going to move on to another section. And I do want to talk about some things before we get to that section. So let's talk about that. Prior to the next section, we need to discuss what we call asymptotes. Right, which you guys knew about these before. We looked at the graphs of the exponential and the log curve. Those both have what we call asymptotes. So you're probably used to the concept. It's like when you're approaching a curve, but possibly you never touch it, but you might cross it every now and then. But eventually, as you go off to infinity, you're just getting closer and closer and closer to some curve. That curve is called an asymptote. So the fuzzy definition, right, not getting too technical here. An asymptote is a curve that a graph approaches as the x or y coordinate tend towards plus or minus infinity. So as you're going off far to the right or far to the left, if you're approaching some curve, that curve is called an asymptote. Or if you're going way up or way down and you're approaching some curve, that's also called an asymptote. So you should know it is possible for graphs to not have asymptotes. Particularly the kinds we care about. So there is a huge variety of asymptotes, but there are only really two we care about. So there's what's called horizontal asymptotes. which we'd abbreviate HA, and vertical asymptotes. We would abbreviate VA. So this pretty much just means when your asymptote is a horizontal line, a horizontal straight line, or a vertical straight line, we will care about when those things happen. Let's take them one at a time. One, to find HAs, how do you go about finding horizontal asymptotes when they exist? Given f of x, compute the following. We are going to compute the infinite limits. Limit as x approaches infinity of f of x, and limit as x approaches negative infinity of f of x. So you're going to find the limits at infinity. Now, how do you know if you have a horizontal asymptote? If either of these limits give a constant value. Say k is the constant value, then y equals k is an HA. Okay, so that's how you'd find it. Otherwise, it's possible that both limits don't exist or they don't give you constant values. F has no horizontal asymptote. Now, there are a couple functions that we like dealing with that we kind of know some things right off the bat. So let me just actually say that. Note. Polynomials do not have HA. Neither VA, by the way, but we'll get there. Haven't told you what those guys are. Right. So polynomials don't have horizontal or vertical asymptotes unless they're lines. Okay. And yeah, so now let's say another function that we care about, if f is a non-polynomial, let me do that, rational function. So remember, a rational function is just a ratio of two polynomials. I don't want the denominator to be a constant because that just makes it a normal polynomial. So we know if you're a polynomial, you automatically don't have HAs or VAs, so you probably don't have to look for them. Just say, oh, this is a polynomial, so it has none. In the event that you're looking at a rational function, a ratio of two polynomials that is not itself a polynomial, then it turns out, then both limits will give same result if it has an HA. And this actually follows by the tricks we have. This follows from the bottom heavy idea. Trick or the ratio of leading coefficients trick. So those are two things. If you have a polynomial, it doesn't have either of these types of asymptotes. Don't waste your time looking for them. And if you have a rational function, you only need technically to compute one of these limits. They'll both give you the same answer. Although I'll probably expect you to write down both of them, even though you're not going to compute both of them. So let's actually do some examples. Example, suppose f of x equals 1 minus 3x squared over 2x squared minus 4. Find its HA or show it does not exist. So this is rational, so I know that they are both going to give me the same answer. So what we're going to do is here is we're going to find the limit as x approaches infinity of our function. It's actually going to give us the same value as we approach negative infinity of this function, which is going to be this is where you guys come in. What's the limit as x approaches infinity of that guy? Anyone? Bueller? You guys have to review your limits. Look at the highest powers. The highest power and the top and bottom are the same. So it goes to the ratio of leading coefficients. That's a constant. It's just a number. This is by ratio of leading coefficients. Right? And so once you get a constant, it turns out that that means y equals minus 3 over 2. This is a horizontal line, is an HA. So horizontal asymptote. That's it. So you should know how to find limits at infinity for ratio of polynomials. I gave you that rule. There are only 3 cases to know. You need to know them. And the cases just depend on what powers there are, how the powers relate to each other in the top and bottom, the degree. Let's look at 2. How do you find the vertical asymptotes? To find them, we say x equals a is a vertical asymptote. If this occurs, the limit as you approach a from the right of f of x is plus or minus infinity, or the limit as you approach a from the left of f of x is plus or minus infinity. Think of, for example, the logarithm. We know that the logarithm curves like this, right? As you approach x equals 0, it shoots down to negative infinity. As you approach from the right side, there's nothing from the left side, but as you approach from the right side, it goes down to negative infinity. This will tell you that for something like y equals ln x, the vertical asymptote actually occurs at x equals 0. But let me give you some tips based on the function that we have, or that we'll commonly use. If f of x is a non-polynomial rational function, the VA occur precisely when f is put in reduced form and we can find x values that makes its that makes its denominator equal to 0, right? X equals such a value is a VA in that situation. Let's do some examples. Example. Find the VA of the following if they exist. Okay, so let's look at two examples. F of x equals 1 over x minus 2, and f of x equals x squared minus 4 over x minus 2. We're going to do these two examples. All right, jumping into A, we have f of x equals 1 over x minus 2. This is already reduced. And x equals 2 makes denominator 0. Right? So you'd literally just set x minus 2 equals 0. This implies x equals 2 is the VA, right? The line x equals 2. And in fact, this graph isn't, the graph of this isn't difficult to graph. Right, that's just like 1 over x, but shifted 2 units to the right. So at 2, we know that the graph looks like this. Right, so you'll see that as we approach from the right, we go up to positive infinity. If we approach from the left, it goes to negative infinity. That definitely fits our definition of what an asymptote is. So it definitely behaves like what we think an asymptote should behave like. Let's move on to B. F of x equals x squared minus 4 over x minus 2. You'll notice here, x equals 2 makes denominator equals 0, but not so fast. F is not reduced. So that's totally irrelevant to us at this point. We have to keep going. So notice that we can reduce you get f of x equals x squared minus 4 over x minus 2. that can be factored into x minus 2 times x plus 2 over x minus 2. And cancel these. And so that becomes x plus 2. So this is the reduced form of f. This is if x is not equal to 2. And that actually just behaves like a straight line. Notice there's nothing that makes that denominator 0. So you would say no VA. No x makes denominator 0. Right? And you could also say that's a polynomial. And again, this guy we actually also know. We've actually used the same example over and over. We know that it's a straight line except when x hits 2. So what happens is we have a hole. And it's at the level 4. But it's not an asymptote, as you can see. It's just a hole. So whenever you have x values that make your denominator 0, but by reducing, you cancel out the factors that would do that, you get holes, right? You don't get asymptotes. So that's why for vertical asymptotes, it's very important that you reduce. Right? So it has to be in reduced form, and we can find x values that make the denominator of the reduced form equal to 0. At least that's how it'll work for us in rational functions. So this has no VA. Let's do one more example. Find the HA and VA if they exist of this function f of x equals 1 over x squared minus 4. This was the last example before the next section, but it's going to be too late to actually start the next section, I think. So let's actually just do this and get out of here. Let's look for the HAs. We know how to find the HAs. We take the limit as x approaches infinity of f of x, but it's rational, so I know this is also going to be the limit as x approaches negative infinity of f of x. What is that for this function? Limit as x approaches infinity of this, what do I get?
0.
You get 0 because it's bottom heavy. And this is because it's rational and not top heavy. So yeah, that's what we get. So now that means that y equals 0 is the HA. Moving on to VAs, vertical asymptotes. So f of x equals 1 over x squared minus 4, and this is reduced. Right? There's nothing you can factor the top or in the top to like cancel stuff in the bottom and reduce it. So what we can do is we realize that this is x minus 2 times x plus 2. So set that guy equals 0. This gives you x equals 2 or x equals minus 2. And these are the VAs, it has 2 of them. And we can see what's going on here. Right, so we have, say, when the graph of this function is going to be, you're going to have a horizontal asymptote at y equals 0, which is the x-axis. Y equals 0, that's the HA. And we have vertical asymptotes in 2 locations. At x equals 2, at minus 2, and at x equals 2. So this is x equals 2, that's a VA. This is x equals minus 2, that's also a VA. Now, this graph, you can know, let me write graph of f equals 1 over x squared minus 4 in green. So what can we do? All right, so I would plug in a random number in the middle to see where the graph is. It is going to be, if I plug in 0, I get minus a quarter. So the graph is here. Now, we know, for example, that this graph does not have any x-intercepts. Why? Because to find x-intercepts, you'd have to set y equals 0. Setting y equals 0 means the numerator has to be 0, but the numerator is 1. It's never 0, so it has no x-intercepts, which means this graph is never going to go up. So it can't do something like this, which is what the asymptote would tell us that it has to do. It has to do pretty much the opposite. It turns out that that is going to be the maximum point. Of course, you'll have to test it, and it goes down from there. Now, other than that, you might wonder, well, what does it look like otherwise? So I want this a little bit to the side more. So what will happen is you can test the random point on the ends. Say plug in 3. You'll notice you would get 1 over 3 squared minus 4, which is a positive number. So the graph should be up here somewhere. Similarly, if you plug in, say, minus 3, you actually will get the same number because you're squaring it. So you know the graph is up here. So you can test the point. Now, once you test that point, you should ask yourself, well, how's the graph going to behave? Could it do something like this, for example? You would say, no, it can't do that for a couple of reasons. It's not going towards the HA. And 2, that would create an x-intercept, which we know does not exist. So that can't happen. I know that the graph has to stay on top the whole time. I also know that it must get close to this line, and it must also get close to this line over time while staying on top, right? So that means the graph must look like this. Similarly, over here, it must look like that. Right, so the green is the graph. That's what that graph would look like. You'll notice it has 2 vertical asymptotes and 1 horizontal asymptote. And that can help us sketch the graph, as you see. We're going to learn to sketch graphs in more detail. That is the next section. But we're not really going to do that now. I'll just post the handout. So I'm going to do 4.3, 4.4, and 4.5 in one because I can. I think one of these sections actually spoke about asymptotes. Maybe it was 4.3 or 4.4, but everything else that you will need, what they talk about in all the other sections, I actually already taught you everything you need to know for the other sections just by how things were organized. But that being said, where are we? Okay, there we go. This is the curve sketching handout. You can find this on the class webpage, actually. Okay, there we go. Can be found on the class webpage. I'd recommend you read it and maybe try like the first example. We're going to do that. Of course, that's an example that you know how to graph already by heart, but I want you to go through the process of doing it that way. We'll probably also do this. I think we graphed C already. And then you can try these. So what I would say is like problems like these is more like what I would put on a final. But from the first section, I would use that for quiz test problems. So yeah, so you can read through this handout. It's again a 6-step process that I would like you guys to go through when sketching stuff. And I'm going to specifically request that you do some of these things or all of these things when sketching graphs in a certain topic. So that's what we'll pick up with next time. So I'll just leave this handout here. You can read through it, maybe try a couple problems and see if we agree tomorrow. Yeah, so that's it. All right, that's it for today. Thank you for your time and attention, and I will see you tomorrow in the next one. Ciao.